Hello everyone, this is Yung Chido. I'm currently working as a PhD student researcher at TU Delft. Here, I'm glad to present our work titled Comparative Study on Supervised versus Semi-supervised Machine Learning for Anomaly Detection of In-Vivo CAN Network. Let's firstly look at the research background and motivation. With the development of vehicular automation and networking, massive electronic control units and various interfaces are equipped in vehicles. In the more and more complex vehicular communication environment, studies had drawn close concerns about vehicular network security to prevent potential attacks from the hackers. For the in-vehicle networking, controller area network, CAN for short, is the most commonly adopted protocol, despite the irreplaceable role and long application history of CAN protocol. It has vulnerabilities, as CAN is designed with transmission through a fixed frequency without security measures against attacks. CAN is weak in the face of malicious hacking. The security of CAN bus is crucial to ensure the safety performance of the vehicle. In the past few years, various anomaly detection algorithms have emerged to identify potential intrusions and attacks. Key challenges and research gaps in this field. In general, there are always far more normal data than anomalies, and in the real world, CAN-based anonymous data generation is always related to safety hazards, which makes it difficult and even dangerous to collect enough anomaly data. Also, labeling the dataset would be a tedious work. Therefore, it would be more suitable to utilize unsupervised or semi-supervised methods to tackle the problem. Then it comes to the research gaps. Although various state-driven machine learning models had been applied to the anomaly detection problem for in-vehicle CAN bus network message, field research had employed unsupervised or semi-supervised methods. Also, there is no comprehensive comparison to evaluate the performance of supervised machine learning versus semi-supervised machine learning regarding this task, where this work tries to tackle these challenges and gaps. In this study, we developed a deep autoencoder-based semi-supervised machine learning for in-vehicle CAN bus network anomaly detection. The framework is illustrated in this figure on the left. The proposed deep autoencoder is composed of the encoder part and the decoder part, which are two symmetrical feed-forward multi-layer neural networks. And the proposed framework, the input data sample are first fed to the encoder part for feature extraction, through which the compressed feature vector is obtained. Then the decoder decodes the compressed feature vector into the original dimension, trying to reproduce the input. To better reproduce the input data, the autoencoder must capture the most critical features regarding the input. This is done by using fewer intermediate hidden layer nodes to obtain the aforementioned compressed feature vector, which removes redundant information and keeps the most vital patterns. Assume that the input data sample can be denoted by X, the compressed feature vector represented by C. Then we can get C by equation 1, where G is the activation function, W stands for the encoder weight, and B is the barriers. Denote the reproduced output represented by X prime. Then it can be demonstrated by equation 2, where G prime, W prime, and B prime are the activation function, weight, and barriers in the decoder part respectively. Then the reconstructed loss between X prime and X can be calculated by equation 3, where else reference the Truden loss function. In this study, mean square error, MSE, are selected. In the training phase, normal data was input to the autoencoder to train the weight, which minimize the reconstructed loss as the objective, and using the backpropagation mechanism as updating method. Then, in the validation phase, a validation dataset that contains a few anomaly data samples is adopted to fine-tune a good threshold of the reconstruction loss. Usually, a good threshold can be expressed by equation 4. Finally, in the application phase, for a new data sample, after feeding it through the trained autoencoder, its reconstruct loss can be calculated and then compared with the fine-tuned threshold. If the loss is beyond the threshold, it will be classified as anomaly, otherwise as a normal one. Then, to make a comprehensive comparison to evaluate the performance of the supervised machine learning versus semi-supervised machine learning for in vivo CAN-bus network data anomaly detection, this study examines traditional machine learning algorithms, including single classifier and ensemble learning models, together with these deep learning models. They are all in the supervised group, while in the semi-supervised group, except for our proposed deep autoencoder-based method, 3 other commonly used models are selected, which are robust covariance, log outlier factor, and isolation forest. Experiments. We tested and verified our proposed method and compared the formation selected models using the IEEE Open Data of Car Hacking Attack and Defense Challenge 2020 dataset. This challenge has 2 comparison rounds, which is the preliminary round and the final round. In this study, for the first time, we built an integrated large-scale training dataset, utilize the training and submission data in the preliminary round, and screen the data with the status of vehicle as stationary, which is the case in the final round. Then, the whole dataset in the final round was selected as the testing set. In this way, we can say the testing set has the capability to evaluate the model to evaluate the model's robustness handling different data distribution. Originally, 5 fields are provided. Based on these fields, this study elaborated 67 features which fall into 4 categories. They are time interval, 1 feature, CAN identifier in decimal, 1 feature, DLC, data length code, 1 feature, and data transmitted in binary values, 64 features. For the data transmitted feature, if the DLC is less than 8, then there are less than 64 bits. In that case, we fill the higher order position with 0. The new but very important feature, time interval, was calculated based upon CAN ID and time step. To be specific, the data was first grouped by CAN ID. Then, within each subset of the same CAN ID, these samples were increasingly sorted by time step. The time interval was obtained by calculating the increasing time step value of the adjacent later sample minus the former one. Finally, a total number of more than 3.3 million samples were obtained as a training set, with nearly 3 million normal instances and 0.3 million anomaly instances, while a total number of more than 1.2 million samples were obtained as a testing set, with nearly 1 million samples as normal data and around 180,000 anomaly instances. Various manners are used to evaluate the overall performance of the selected models. We first obtain 4 basic terms. They are true positive, true negative, false positive, and false negative. Then, based upon these 4 terms, accuracy, precision, and recall are calculated using these equations. Another significant indicator, which is the receiver operating characteristic area under the curve, ROC AUC for result, to measure ROC AUC one in diagnostic sensitivity, which depends on the true positive rate, also seen as the recall ratio, and the specificity, which is expressed by the true negative rate. They are calculated by these 2 equations. Experiment results and comparison. In this slide, we synthesize the quantitative performance comparison results of the selected models in the table on the left. As we can see, supervised methods generally outperform semi-supervised methods. This can be explained by the truth that they utilize more information. Typically, XGBoost algorithm in the supervised category shows the optimal performance among all compared algorithms, with the best accuracy, precision, and ROC AUC. These results also beat the best score reported in the regional car hacking attack and defense challenge in 2020. To better visualize the results of XGBoost, the figure on the right demonstrates its confusion matrix from which one can identify the correctly classified number of normal and anomaly instances. From the table, it is also noticed that although all semi-supervised models do not behave well, the proposed DAE-based method obtains the best performance among the ones in the semi-supervised group. This figure visualizes the reconstructed loss obtained from the deep autoencoder-based semi-supervised learning method. It can be seen that a large proportion of the anomaly data instance will obtain higher reconstruction loss compared with the threshold. However, there are still anomaly data samples that deliver very low losses which follow the algorithm. These findings somehow verify the potential effectiveness of the proposed deep autoencoder-based method. To further verify the effectiveness of the elaborate feature engineering method and extracted the variable features, and also the best method of the developer XGBoost model, population studies are carried out. In this figure, the relative importance of utilizing features when we use XGBoost are illustrated. The first 64 features are data transmitted, and the last 3 features are DLC, identifier ID, and time interval respectively. One can identify that the most important feature is our proposed newly calculated time interval, while the data transmitted expressed in the binary value also important. However, these variable features are not covered in previous study using similar data sets. Furthermore, in total, 3 XGBoost model variants are tested in the ablation study. XGBoost 3 is the XGBoost model using only the last 3 features, where XGBoost 66 means the XGBoost model using the first 66 feature without our proposed time interval. It is witnessed that without time interval, our evaluation metrics of XGBoost 66 decrease a lot compared with XGBoost using the full 67 features. And even XGBoost 3 outperforms XGBoost 66. These findings further demonstrate the importance of the proposed time interval feature. Finally, this slide summarizes the main contributions of this paper and propose possible further research directions. For contributions, firstly, this paper developed an effective feature engineering technique, extracted and designed new but variable features applied for the in-vehicle CAN-bus network data anomaly detection. Secondly, this paper proposes the deep autoencoder-based method applied for this data anomaly detection task. And the proposed deep autoencoder-based model also performs other based on semi-supervised models. Thirdly, this paper draws a comprehensive comparison between supervised machine learning versus semi-supervised machine learning applied for the in-vehicle CAN-bus network data anomaly detection. Finally, the developed XGBoost-based model using the extracted variable features obtained the state-of-the-art performance with the best accuracy, precision, and ROC AUC, beating all other models reported in available publications. For future work, we would like to upgrade the developed semi-supervised learning model, improving the robustness and adding interpretability. We also want to transfer the model developed and the knowledge learned for abnormal driving behavior detection, which can be helpful to improve traffic safety. Lastly, it is worth to delve in the fast-developing fields of learning and meta-learning applied for anomaly detection. Thank you for watching this video. If you get any questions or want to copied on certain future research topics, please email me.